For
Okay, let's get started. Did you miss me? So I hope that everything has gone smoothly during the time that I was gone, that both treated you well. Apparently there were some audio difficulties on the lecture last time, so I've heard that it didn't work so well on the recording either. So if you wanted to review the material by listening to the recording last time, I've heard that it's not gonna, it doesn't work so well. So I'm hoping the audio issues have worked out. I asked the mic still sounds over good. All right, so we'll get fiddle with the mic. Okay, so how about that? I've changed the mic setting to the setting it's typically on. Much better. Okay. Maybe I could just talk really loud and overdrive the mic that way. Okay, how about that? So, anybody have any questions? We have an exam coming Friday, right? Take-home exam. I intend to give a review session on Wednesday. Today we'll review a little bit of what you talked about last time and carry it on to the next step of priority inversion. So, what is it? Lab 7's due tomorrow? Right? Semaphores? You can hand it in on Thursday, that's fine. There's provision on Blackboard for allowing that to happen. Comes with a big black bold late next to it. Only a minor penalty. A few percentage points. So, anyway, just a few tricky parts about that one, making your priority scheduler look like it's working like a fair scheduler. Good stuff. I'll have office hours today. So, no questions? Yeah.
So each sample prior to, we just sort it before it goes into the queue, and then just pop off the top one.
So the question is, should you sort the priority queue going in, and then when you're removing, pop off the top one? That's one of the two options that I said you can do. You don't have to do it that way. You can sort when you can search for the highest priority process when you're looking for it, and just maintain an unsorted queue if you want to. But I contended last time around that maintaining a sorted list is probably a little bit better. Okay. Who?
When you set the priority, you do that when you're creating your FIFO, and you can do that however you want to.
When you set the priority of a process, you don't do it in the FIFO. When you set the priority of a process, you set it when you create the process. It's a part of the process, not a part of the FIFO. The FIFO just reacts to the priority of the process that you're putting into it. So in proc create, you would pass a field that would be the process's priority. Okay? Other questions? Okay. Lab 8 is going to be posted tomorrow. Good stuff. You already have all the material covered in lecture that you're going to need for Lab 8. That'll be the table-based scheduling and utilization-bound analysis. This stuff that we're talking about is Lab 9. It's response time analysis. You'll need Lab 9 is the last one. So we will be covering this material. This is the first half, the response time analysis and the priority ceiling protocol. That's the first phase of Lab 9. The second phase of Lab 9 is having to do with RS-232 and implementing a software UART. And we'll be lecturing on that after the exam. But here it is before we give out Lab 8. You already have enough material to start. You will already have enough material to start Lab 9. So anyway, we're way ahead in lecture. Okay. So what I'm going to do, I'm going to start at the beginning of these notes, these real-time scheduling 2 notes that Rohit lectured on last time. And I'm just going to blast through them fairly quickly and get down to the end showing an example. So I am going to be repeating some of what Rohit talked about, but just for the intent of giving a review. Okay, so if you remember what we're talking about, RMA stands for rate monotonic analysis. RMS, rate monotonic scheduling. And you remember what rate monotonic scheduling, rate monotonic analysis is all about? So the whole point is we're trying to prove, given a set of tasks, that they will always meet their deadlines. Okay? The initial baseline proof, proven by Liu and Leyland in 1973, was the utilization bound. So utilization bound is saying if you underutilize your CPU by enough, then we can guarantee that you will always meet your deadlines under certain criteria. Those criteria include you have a set of independent processes, no shared critical sections. Those independent processes are periodic. Those independent processes have a worst case execution time. We assume negligible scheduler overhead, and we assume that every process has to complete by a deadline. We assume that that deadline is equal to its period. So you invoke a process, it does its work, and it goes to sleep. Every process has to complete the amount of work that it's got to do before it's invoked the next time. The amount of time between one invocation and the next invocation is fixed, and it repeats. Okay? So then the utilization bound criteria specified by Liu and Leyland is the following. It says, if you compute the ratio of a process's compute time to its period, and you sum up those ratios for all of the processes in your process set, which you've got n processes. So you sum up all those ratios. If that summation, we'll call this the utilization bound, if that utilization bound is less than this upper bound, where you take n times the quantity 1, or times the quantity of 2 to the 1 on n minus 1. And again, this is not a factor of what are the compute times of the processes. This is not a factor of the periods of the processes. It's not a factor of what type of processor you're running on. All that it is just saying the number of processes. So if you've got 10 processes, this bound is a factor of the number of processes you have. So 10 times 2 to the 1/10 minus 1. If this ratio is less than that, then you have a proof of schedulability. Okay? But there's a lot of ifs in this situation, because we said all your processes have to be independent. All your processes have to be periodic. All your processes have to, the other if is that we have to assign priorities to processes. Those priorities can't change. This is fixed priority scheduling. And you have a priority scheduler. Each process is assigned a priority. No processes share priorities. So we just specify if this ratio here is less than this upper bound, and this upper bound asymptotically approaches about 70%. Okay? So if the total percentage of the CPU that I'm utilizing, given the set of processes that I have, is less than 70% of the total CPU time available, then I have a guarantee of schedulability. So what that means is I have to, in order to make this work, I have to let my processor sit idle at least 70% of the time, or 30% of the time. I have to make sure that I've got too much processor for the tasks that I'm using in order for this guarantee to apply. So what we're saying is this is pessimistic, but it gives you a proof. Okay? One of the goals that we're doing with response time analysis is we're attempting to address the pessimism in the utilization bound analysis. We want to with embedded systems, we have tight timing constraints, tight cost constraints, tight power constraints. If we have to underutilize our processor to such a degree that we're just sitting idle 30% of the time or more, in order to guarantee that our system's schedulable, well, that just burns us. We don't want to let our CPU sit idle. That's extra clock cycles that theoretically we could be doing something useful with. You have to overbuy your CPU. It has to be more powerful than what you need. So what we want to be able to do is come up with some alternate mechanism to proving whether or not our system is schedulable, so that we don't have to underutilize our processor to the degree that the response time analysis with the utilization bound dictates. Okay. This is sufficient but not necessary. What do we mean by sufficient but not necessary? If your set of tasks meets that bound, then you guarantee schedulability. It isn't required that your set of tasks has to meet that bound in order to guarantee schedulability. You can have a set of tasks which are provably schedulable, which violate that bound, and I'll show you an example of one as we go through this proof of response time analysis. So, if your set of tasks meets the utilization bound analysis, you have a proof of schedulability. If you can meet the criteria, you can always use utilization bound analysis to tell you whether or not you're going to meet schedulability. But it isn't required. There are alternate ways. Okay? So we're going to derive such a way with a response time analysis. Okay. Response time analysis offers a schedulability proof. It is both necessary and sufficient. So if you violate the response time analysis, if the response time analysis says you're not schedulable, then you're guaranteed not to be scheduled. You're guaranteed not schedulable. If the response time analysis says that you are schedulable, then you have a proof of schedulability. Okay? So both necessary and sufficient. This means that it'll tell you when you work, and it'll tell you when you won't work. All right. We define response time. R sub I is the response time of a task. That is the time that it takes for when a task is released. The worst case response time is in the worst case. When a task is released, how long does it take to finish its work? So it's got a certain amount of work it's got to do before its period gets up and it has to be re-invoked. We know that it's got a worst case computation time, WCET, or the compute time, CE. The compute time is the amount of work that a task has to do. It takes it longer than that compute time in order to do the work it's got to do, simply because it can be preempted by some higher priority task. So you get released, you've got to do X amount of work, but you might have to wait in order to get your turn to use the CPU in order to be able to access the CPU. So the response time is what's the sum of all the time that I've got to wait plus all the time that I spend working before I actually finish. So I get released, I finally finish, how much time elapses from there? And then the proof of the response time analysis is if I can find the worst case response time for each of the tasks in my system, and I can compare the response time against the task's deadline, if I can prove that my worst case response time is always less than my period, I have a proof of schedulability. I can say that no matter what, if in the worst case, this task's response time is always less than its period, then it will always be schedulable. Okay. So what we want to do is derive this idea of response time. We factor in response time saying that under our current model, where we don't have process interaction, what we have is two factors in CPU time. From a particular process's perspective, this process is the highest priority process. As soon as it gets released, it gets the CPU. It gets to start executing, it gets access to the CPU. When it finishes its work, it finishes. The highest priority process's response time is always equal to its compute time, simply because nobody else can preempt it. It wins. Okay? If it's a pig, it gets to be a pig, it gets to eat the CPU time, and we just are happy with that because we are biased towards highest priority processes. If we have a process that is not the highest priority process, when it gets released, it gets the CPU so long as no other higher priority process is asking for the CPU. If no other higher priority process wants the CPU, it's the highest available, and it gets to have access to the CPU. However, it may be just put into the queue, and there may be higher priority processes that want the CPU. So if those higher priority processes want the CPU, this lower priority process has to wait. The time that a process has to wait in order to get the CPU, due to the fact that higher priority processes are available and ready, and they get the CPU because they're in line ahead of me, that's called interference. Okay? So interference time is a time where I'm preempted. I'm ready, I'm waiting for the CPU, I'm on the ready queue, but there are people with higher priority that are ahead of me. So interference time. So therefore, for a given task I, its response time is the sum of its compute time with its interference time. We calculate interference time, the total amount of time that all of the processes with higher priority than me interfere with me. So if they get their work done and they're asleep, and then I become ready during the time which they're asleep, that doesn't count as interference time because they're not preempting me. They're asleep, and I'm sneaking around them while they're sleeping. Okay? Interference time only factors in those tasks which are available, ready, and wanting the CPU with higher priority than me. Okay. So if we assume that we have I sub I, R sub I, and C sub I are as bad as they can get in the set of tasks that we have. So in the worst case interference time, worst case response time, worst case execution time, what we want to do is prove for all tasks in my system that the response time of that task is less than or equal to the period of the task. All right. Now the rationale behind response time analysis came in this graph. I don't know if Rohit went through this one, probably did. Okay. So the whole idea here is you've got two tasks, task J and task I. Task J is higher priority than task I. Task J runs, since it's the highest priority process, when it runs, it gets to have the CPU completely until it's done with its compute time. So when both of these tasks are released, task J runs and completes its execution. That happens at C sub J because it takes C sub J ticks of time in order for task J to complete. Task I has to wait for task J. This time right here where task I is not running because task J is running is accounted for in the interference time of task I. Okay, so it's interfered with based on task J because task J wants the CPU. As soon as task J is done, it goes to sleep. It sleeps until it gets released again. It gets released again based on its period, T sub J. So T sub J occurs, task J gets released again, it gets the CPU, and it runs for a while, and then it goes to sleep again. After it goes to sleep again, task I gets to run again. At 2 times T sub J, task J gets released again. So there's these various times in which task J gets released. Task I gets released at the same time that task J's first release occurred, and so it runs on it gets the CPU. It wants the CPU for a longer chunk of time than task J does, but its period is also longer as well. So task I runs when task J doesn't want the CPU, then it runs again when task J doesn't want the CPU. Again, these aren't separate releases of task I. This is just, I've started my work, I've still got some more work left, but task J gets released, and so I have to wait for task J to be done. I resume my work over here, and then I get interfered with as task J again, and then I finally resume my work again, and finally I finish. At this point I finish my first invocation of task I. At that point we say that the response time of I is this tick over here on the time axis. The total time from the release point to when it finally finishes its work for that release. Okay? The response time of J is C sub J. It's equal to, because task J gets released here and it completes there. It gets released here, completes there. Released here, completes there. There's only one release of task I on this whole timeline. Make sense? Hope so, because this is the second time you're hearing it. Okay. So how many times will J preempt I? If we divide the response time of I, so the total time that it takes I to complete, by the period of J, that'll tell us how many times J will interrupt I. So we take the ceiling of that. That tells us, so the ceiling of these two, that tells us the number of times that process J can interrupt process I and execute while process I still wants the CPU. Each time J is released, how much time is used? J computes for C sub J ticks of time every time it's released. So therefore, we can compute the total interference on I due to J as the ceiling of Ri on Tj times C sub J. So therefore, we calculate in this two-task system the response time of task I as the interference time of I due to J plus the compute time of I. Okay. Now, if we have multiple tasks, not just two tasks, all that we do is we just take the sum. When we're computing the interference time of task I due to all the other higher priority tasks that have higher priority than I, we just take the sum over the set of higher priority tasks that have higher priority than I of the interference time of that task on task I. So we just say, for J in the set of higher priority processes based on I, we take the ceiling of R sub I over T sub J times C sub J. Now this just kind of works out because what you're doing is you're saying, okay, how much interference do I get from task I based on task J, the highest priority process? Then what's the interference time due to the next highest priority process and the next highest priority process? And I just consider each one of those individually. I don't have to worry about this cascading effect where, well, what happens if the third highest priority gets interfered with by the second one and then by the first one? by the nature of the fact that I go and I calculate what's the interference time of the highest priority, then the second highest priority, in this summation, that factors all of that cascading interference into these equations. So I can proceed from that point. Okay. So the response time of I, R sub I, is equal to C sub I plus the summation of the interference time. So then, how do I calculate the response time? The problem is we've got this R sub I that appears on both sides of this equation. R sub I is the result, and R sub I is in this ceiling function. And the problem is, normally what we would do is we'd pull out our good old friend algebra and start doing summations and divisions and putting things on both sides, and we try to collect all the R sub I's on one side and everything else on the other side. How do you undo a ceiling function? Floor it. What do you think this is? A sports car with no seatbelt? We have C here. Oh, wait. Okay, so you don't. It's just a pain. So what we're going to do is we're going to solve this using a recurrence relation. Those of you who've had discrete math know what a recurrence relation is all about. Those of you who listened to Rohit last time should also know what a recurrence relation is all about. So that puts everybody in that set, right? We're all good with recurrence relations. Anybody willing to admit not good with recurrence relations? Good. Okay. We actually have volunteers. I should make it in Dr. Moon style. Come to the board and work it out. What the recurrence relation is we're going to first observe the fact that we don't know what this value is here, this R sub I. We're going to compute it. But if we can say, I'm going to hazard a guess at what it is, and I'm going to see what the result is if I guess. So if I put a guess in for what the response time is on the right-hand side of this equation, and then I compute what the left-hand side of the equation will be, and then I use that result and use that as the next guess, and then I compute what the result will be, and then I use that result as the next guess, and I put it in here, and I see what the result will be. The idea with solving a recurrence relation is eventually I'm going to get a value from one of these results that I use as a guess that'll give me the same result. And when I get to that point, when my result of inserting a guess is the same number as the guess itself, that means the recurrence is solved. That means I've got an answer. So I just keep iterating this guess and get a result and guess and get a result and use the result as the next guess and so forth until I get convergence where my guess value from last time is equal to the result from this time. Does it always converge? No, it doesn't always converge. And if it doesn't converge, then that tells you something about the problem. And there is a criteria, there's a particular criterion that dictates when you're done. You will eventually be done with solving the recurrence relation. Either you'll get to the set point to where your Wi, n plus 1, is equal to Win for some n, or you'll prove that the system doesn't meet a deadline. Okay? One of those two will occur. Sometimes it takes multiple iterations. We don't know how many iterations it takes. You're going to write a computer program that does it. I have 9. Okay. The reason why this works is because when you put in a guess right here, first off, response time can't be negative. It can't be a negative value. What that means, if you think back to what are we solving, we're solving a system that we're trying to figure out how many clock cycles does it take once I release a process before it finishes. Or how many seconds does it take, whatever unit of time. How many units of time does it take once I release a process before it completes? So you can't have a process take negative units of time. That doesn't make physical sense. Okay? So, first off, these response times are going to be positive numbers. They don't have to be integers, but they're going to be positive numbers. If you look at the structure of this equation, T sub j is always a positive number. C sub j is always a positive number because every process has a positive compute time, and we always have positive periods. The values associated with this, because of the fact that all these numbers are positive, when you hazard a guess here, this result will either be equal to or bigger than the guess that you used. So this equation is monotonically increasing. Okay? So each iteration you'll get a bigger result. And so that's why the recurrence relation works, because if you end up getting a bigger and bigger and bigger and bigger and bigger and bigger and bigger result, eventually you'll get to a point to where the response time that you're calculating is bigger than the period that it's supposed to fit into, and you've just proven that this isn't going to work. Or alternatively, it'll get bigger and bigger and bigger and bigger, and finally it'll flatten out and get to a particular set point value. And as soon as it gets to that set value, you know you've established what the response time is. But you still have to check that resulting response time against the period to see whether or not it works. Okay? So this guy, this recurrence relation, is an implicit loop. So you're going to grab and guess a value, put it in for Wi sub 0. This n is going to be your loop counter. So Wi 0. And you're going to calculate Wi 1. Okay? And then the next iteration, you'll put that Wi 1 here, and you'll calculate Wi 2. And then you'll grab Wi 2, put it in here, and calculate Wi 3. And you'll keep going in there until you get to a point where W sub n is equal to Wn plus 1. That's solving the recurrence relation. You're not using algebra and finding this and getting a result. You're iterating until you find a set point. Okay? So the whole idea is to pick a good value, a good initial value for your initial response time guess, and then proceed iteratively until you get to a set point. So what's the value that you should use for Wi sub 0? Your first naive implementation, you could just say, I'm just going to guess that the response time is 0. That means the process completes immediately as soon as it starts. A better guess would be, I'm going to guess that the response time can't be any less than the process's compute time. If you remember, a process will have to compute for at least the amount of time that it's got to compute for. It might have to wait, in addition to that compute time, the interference time due to higher priority processes interrupting it. But we know that at least it's going to take C sub I, the compute time for this process. So we're going to say that an initial good guess for our response time for a task I, Wi 0, should be equal to the compute time of task sub I, the C sub I, or the compute time for task I. Okay. All right. When do you stop doing the computation? You stop doing the computation if you ever discover that Wi sub n for some iteration n is greater than T sub I. T sub I is the period of the task. You remember that we have to make sure that the response time of the task has to be less than or equal to its period, because that's our deadline for the task. So if we ever discover that one of these intermediate values says that our response time is bigger than our period, it doesn't matter if we've achieved a set point by that time. We know because the function is monotonically increasing, we're never going to get to a point to where it says, oh, if this is 10 and Win tells me 13, we're not going to get Win plus 1 be 8. It'll never turn back around. Every subsequent Wi value will either be bigger than or equal to the current one, because of the fact that that equation is monotonically increasing. Okay, so here's an example. This is out of the book. Process A, B, and C. Process A has a period of 7. B has a period of 12. C has a period of 20. Process C has a compute time of 3. B has a compute time of 3. C has a compute time of 5. If I remember correctly from what Rohit told me, you didn't go through the example, right? Okay. So let's assign priorities to these tasks. How do we assign priorities? Should we all assign them priority 1? Okay, should we all assign them priority 10? Okay, you're giving me lots of no's. What should we do? Give a unique value. Okay, so we'll say 30, 31, 32. 32, 31, 30. How should we assign priorities? What is the rate monotonic priority assignment criterion? Number 1, it can't be the same. What was that? Lowest period gets highest priority. Okay, Gautam's claiming that the process of lowest period should get highest priority. What happens if process C is the most important process in the system? Should I assign it the highest priority? No. Doesn't matter importance. Fixed priority scheduling with rate monotonic criteria dictates you have to assign priorities based on period. And that is the only reason you assign priorities. It's not based on how important it is. Even if this guy, if he fails to run, the whole system is foobarred. Doesn't matter. You assign it strictly based on the priorities. Why? Because that's critical to our proving schedulability. Okay? So that assumption is woven into these proofs. You have to assign priority based on period, where the lowest period gets the highest priority. Why the period? Because the period is a deadline. We're actually assigning it based on deadline. And because of the fact that we've said the deadline of the process is equal to its period, the soonest deadline or the nearest deadline gets priority. And when I say soonest deadline, that is not a dynamic priority where I run my scheduler and I say, okay, which process is going to crash first? Let me run that one first. That is a different dynamic priority scheduling technique, and we'll talk about that later on in the semester. What we're doing is we're just saying, okay, which of these processes, given their periods as such, are we going to, which process will end up having to be reinvoked first? So process A with the gets highest priority because it has period of 7, then process B, then process C. So we'll just assign them priorities 1, 2, 3. Again, do note that because of the fact that we're using low numbers for high priority, that's backwards than what the book's talking about. The book's wrong. I'm right. It's good to be the king. Okay, so let's calculate the response times for these various tasks. We're going to calculate the response time of task A. The response time of task A we compute by observation. Why by observation? Because it's the highest priority task. Whenever it gets released, it gets the CPU. No questions asked. Why is that the case? Because we have independent processes and there's no ability for a lower priority process to execute when the higher priority process wants to run. No semaphores, no ability to block a process, so therefore our A, whenever A runs, it gets the CPU, and it gets the CPU until it's done with the work that it's got to do. So the response time of A is equal to its compute time, or 3. Okay. In order to compute the response time of B, we have to use this recurrence relation. The reason why is because when B runs, it potentially could be interfered with by the fact that A has to run. So we start with this recurrence relation, and we say, okay, well, what's a good guess for what the what's a good guess for the response time for B? Well, we know that the response time for B can't be less than its compute time. Its compute time is 3, so we'll say WB0 is equal to C sub B, or the value 3. Okay. Next, what we're going to do is iterate with this recurrence relation and calculate the next guess for the response time of B. The next guess we'll label as WB1. That's equal to C sub B plus the ceiling of WB0 over T sub A times C sub A. Now wait a minute, am I pulling a fast one here? There's no summation. Remember the equation had a summation over there. We don't see a summation here. You remember the summation said, I'm going to sum over all of the processes that have higher priority than the task that I'm examining. So in order to compute WIN plus 1, I examine the compute time of I and add to it the sum of all these ratios based on the set of processes that have higher priority than task I. Okay? So when J is in the set of processes that have higher priority than I. If we go back down to our example, what's the set of processes that have higher priority than process B? Just process A. We don't need a summation because there's only one process there. So we just compute it for the one process. Okay. So so what we end up with here is this equation. WB1 is equal to C sub B plus WB0 over T sub A, the ceiling of that, times C sub A. Again, this is just writing down the formula with knowledge of the fact that we don't have a summation. So if we plug the numbers into here, for WB0, we use what we wrote down up here, this 3. T sub A is the period of A. We looked that up in our table. That's a 7. 3 divided by 7, the ceiling of that, times 3. C sub B is 3. So we times the ceiling by 3 because that's the compute time of A, again, looking up in our table. So 3 plus the ceiling of 3 over 7 times 3 is equal to 3 plus 1 times 3. I claim that this is 1 times 3 because 3 over 7 is less than 1. You take the ceiling of that, that gives you the next integer greater than or equal to the ratio there. So that gives us a 1. So that's 3 plus 1 times 3, or in other words, 3 plus 3, that equals 6. All right, now the next step is we ask ourselves, are we done? 6 is the value for WB1. The value for WB0 was 3. Is 3 equal to 6? 3 is not equal to 6. So therefore, we don't know what the response time is. We have to recurse. So we proceed to calculate WB2. So WB2 looks as follows. WB2 is equal to C sub B plus the ratio of WB1 over T sub A, the ceiling of that times C sub A, or in other words, 3 plus 6 over 7, the ceiling of that times 3. That's 3 plus 1 times 3, or 3 plus 3 is equal to 6. What we have now here is WB1 equals WB2. So this was 6, that's 6. They're both 6. We can stop. The reason why we're going to stop is because if we tried to calculate WB3 and we plug a 6 again for right there, we're going to get the same result. Forever and always on this recurrence relation, it will give you 6, 6, 6, 6, 6, 6, 6. So because of the fact that WB1 is equal to WB2, and that's equal to the value 6, we conclude the response time of process B is equal to 6. Okay, now process C. Now this gets a little bit more fun, because now we have two processes with higher priority than process C. We're going to have our initial guess, WC0 equal to 5, because that's the compute time of process C. Then we solve this recurrence relation, WC1 equals C sub little c plus WC0 divided by T sub A times C sub A plus WC0 over T sub B times C sub B. These two guys are just a summation written out without the sigma, okay? So A is a higher priority than C, B is a higher priority than C, so we have to account terms for both of those situations, okay? So this term right here involving the little a's, that says how much time does A running interfere with process C. This one says how much time does B running interfere with process C. So these two are both calculating interference from higher priority processes on C. So if we plug in the numbers from there, we end up with 5 plus 5 on 7 times 3 plus 5 on 12, ceiling of that times 3, and we end up with a value of 11. And we ask ourselves, is 11 equal to our initial guess of 5? No. So we recurse again. We calculate W2 sub C. Again, same equation, just plugging in the new value for WC sub 1 into where we had WC sub 0 before. So 5 plus 11 over 7 times 3, 11 over 12 times 3. That's 5 plus 2 times 3 plus 1 times 3. That gives us 14. 14 is not equal to 11, so we recurse again. We use 14 in the slot for what our estimate of the response time for process C is, and we proceed with the computation, and we get 17. 17 is not equal to 14. We recurse again. WC sub 4, plug in those values, we end up with a value 20. 20 is not equal to 17. We go again. WC sub 5, we end up with this, to where we plug in the 20 over 7, 20 over 12, calculate the ceilings, and we end up with a value 20. So WC sub 5, WC sub 4, both of those are the value 20. Therefore, we conclude that is the correct response time for C. Now we do the check. What we have to do is we say, okay, what's the period of each of the processes? What is their calculated response times? And do we know whether or not the response time is less than the period? So we say, okay, the period is 7, the response time is 3. Again, this is worst case response time. So because of the fact that the worst case response time is less than the period, that means that that task A will never have a response time that's greater than its period. We can say that the task A will always meet its deadline. Task B has a response time of, or has a period of 12, a response time of 6. Again, similar situation to where the response time, worst case response time, is always less than its period. Therefore, we know that task B will always meet its deadline. The response time for task C is 20. Its period is 20. This is what you call cutting it close. because the response time is equal to its period in the worst case. So the proof works out, but depending on the granularity of the units of time that you're using and the overheads involved, if the units of these guys are microseconds and your scheduled overhead is just, not negligible necessarily, the overhead might nudge your response time past its deadline when you're running task C and could cause you to miss a deadline. This is a case where you'd want to worry about your system if the response time is equal to its deadline. But nevertheless, the mathematics tells us it is proven. The mathematics doesn't factor in scheduled overhead. So that's one region where you'd want to pay attention to where your abstractions break down. Now, if we consider these set of tasks could be applied to the same utilization bound analysis that we talked about that Lou and Leyland developed before, where we can take the ratios of the compute time. So if we take the compute time to the process's own period and sum those up for all the tasks, we have 3/7 plus 3/12 plus 5/20. In other words, 0.428 plus 0.25 plus 0.25. That gives us 0.928. For when capital N is equal to 3, the utilization upper bound computes out to 0.78. So what we're saying is we're using 92.8% of our CPU time with this set of tasks. The response time analysis, the original utilization bound test, tells us we can't use more than 78% if we want that proof to apply. We have a proof of schedulability, so we can be confident that our set of tasks will indeed work, but the utilization bound test fails. So that's just an indication that you can have sets of processes that fail the utilization bound test, but which are still schedulable. This is an example of one. If this number here that we calculated with the utilization-based test would have been less than this other number, this 0.78, that would have given us a proof. And given that proof, we wouldn't have had to do all this recurrence relation shenanigans. What this tells you is that the amount, so one thing that you should know is the amount of math you've got to do here versus all the pages of math we just did up there, this is much easier. Use this when you can. Don't go to the recurrence relations unless you have to, especially on an exam, because you will use a lot of time. And I had many people on a final exam last year dive straight into response time analysis and spend a whole lot of time doing response time analysis when all they needed to do was a utilization bound test. Okay, so that is response time analysis. Any questions on it? I should say this is response time analysis for independent processes. Our next step is when we have processes that have critical sections. Okay, onward and upward. Bet you didn't know this class was going to turn into a math class, did you? There are those in the class who say, Dr. Please make it stop. Please make it stop. Let's go back to programming. Okay. Y'all are asleep now. I'm sorry. Okay. So we're going to consider priority inversion. Priority inversion is what you call a big problem. Some of it's tolerable, some of it's not. And I'll show you examples of why not. Okay? Up until this point, we've assumed that all of our tasks are independent. So we are retaining the idea that all of our tasks are periodic, that we're doing fixed priority scheduling, and that priority is assigned according to the rate monotonic criteria of having the processes with the lowest period getting higher priority. So the question that we have to address is, can resource or critical section sharing impact schedulability? So let's consider the following example. We've got two processes, A and B. Okay, so process A is higher priority than process B, and we've got squiggly lines and blacked out sections. So we're going to assume that a process, when it runs, it's going to run for a little bit, and it'll grab a semaphore. The reason why it grabs a semaphore is because it's going to enter a critical section. That critical section maybe it's going to call printf. Well, if we're calling printf, that black region would be across the page. But it's going to access some shared resource. That shared resource must be protected to make sure that while a process is executing within that critical section, another process does not preempt it and access the same critical region while the first process is inside. So we have to protect that critical region. So a process will run for a little bit, grab a semaphore that protects the critical region, and we're talking here about strong semaphore, so we're blocking processes. Okay, so we grab a semaphore that protects the critical region, and we execute the critical region, and then as soon as we're done, we release the semaphore, and we proceed executing without owning a semaphore. Okay, a little bit different than what you're doing on Lab 7, where you're executing most of the time while owning the semaphore. So here we have regions of execution before we get to this blacked out box. This is where A is running without owning a semaphore, and inside this black region, A is running while owning a semaphore, and then it releases that semaphore, and then it continues to run doing other work that isn't a critical section, and then it completes and goes to sleep. So C sub A includes all of the time where A is running, including the time where it's running with a semaphore and the time where it's running without the semaphore. So it wants the CPU for this whole time. That's all of its compute time. It just so happens that a chunk of it is where it wants a semaphore. Okay. Likewise for B. We can run for a little bit without owning a semaphore. It just so happens that B wants to own the semaphore for more clock ticks than A. So A just wants to run it for one little chunk of time. B wants to run it for 3 chunks of time. Okay, so under one circumstance, we could run the processes as follows, where A gets released at tick 0. A runs for a little bit and then finishes, and sometime during this point in time where after A gets released, B gets released, but it's blocked waiting for the CPU. As soon as A completes, B gets to access the CPU, and so it starts accessing the CPU, does its execution, grabs the semaphore, executes with the semaphore, releases the semaphore, finishes its work, and then at some point here it'll get preempted because this is the period of process A. Process A gets to run, grabs the semaphore, finishes, and then it allows B to be able to finish its work. So when you have a graph like that, everything's working great, the processes are working together, A gets to run whenever it wants to, B gets to run whenever it needs to, subject to the restriction of priority. So the issue is if B only gets preempted when it doesn't own Q, then everything works just fine. However, if you have the following scenario here, where A runs, grabs the semaphore, releases the semaphore, finishes its work, then B runs for a while, and then grabs the semaphore, is in the middle of the execution of the critical section. It hasn't finished the critical section yet, but let's suppose that at that point, that's where the period of process A occurs, and so process A gets released again. So at that point, process A gets to run. B gets preempted. It still owns the semaphore, but it gets preempted because A is higher priority. A gets to run for a little while, and then we get to the point in its execution. So you remember, after it runs for a little bit, it asks for the semaphore. So at this point, it asks for the semaphore, but it's not available. So process A gets blocked. Process B gets to run. Why does B get to run? Because A has to wait for the semaphore in order to occur. So B gets to run. B runs, completes its execution of the critical section, releases the semaphore. As soon as it gets released, that grants ownership of the semaphore back to A, and A gets put back on the ready queue. And since A is higher priority than B, A gets the CPU, B gets to be preempted. So A now gets to run, owning the semaphore, then gives up the semaphore and finishes its execution. And as soon as it finishes execution, it goes to sleep. Then control transfers back to B because B is the next highest priority process available and wanting the CPU. So what happened here is, for this one little chunk of time, we got to run B as if it were the higher priority process. Okay? This is a priority inversion because B has a lower priority than A, but yet it gets to run instead of A. Is that a bad thing? In this context, no, it's not. Because even though we have priorities set up, we have to protect the critical regions. Protecting the critical regions is, well, critical. So if we didn't have a situation like this set up, then somehow what we would do is just allow A to run and A to enter the critical section in the middle of the time where B is running and entering the and accessing the critical section. We violate the bounds of the critical section, the program crashes. You've just crashed your plane, or you've hit the bus, or some bad things are happening. So we have to make sure that we protect the critical region regardless of priority. So we set this up and we claim that's a good thing. The reason why it's a good thing is because we protect the critical region. There is a problem that I'll tell you about in about a week, where maybe we'll lecture on Friday on this. But anyway, there's a problem where this priority inversion can lead to really bad things, to where you have a complete priority inversion across all the processes. So we'll talk about that one next time. We are reviewing in class on Wednesday. I don't think I've posted a practice exam yet, have I? I will post that so that you guys can take a look at it. Be prepared to ask questions on Wednesday. And don't just be, well, what's on the test? It's all on the test.
What?
Welcome back.
Yeah.